my name is Isabella and I will be your host for this mathematics video brought to you by RJ. So today I ask you, what is the height of a simplex? Before we figure out what the height actually is, we must define a few other terms. Definition: an n-dimensional regular polytype with n plus 1 vertices. A simplex is actually what is being constructed in the previous video. Regular definition: all edges are equidistant. The edges are the line segments between two vertices or points. Polytope definition: a closed geometrical object consisting of finitely many points that bound an n-dimensional space. By closed, I mean its surface is connected and all of their surfaces are connected and so on. Base definition: one or more n-1 polytopes which serve as a foundation for constructing a n polytope. Since n represents the dimension, I'm going to shorten n-dimensional polytope to just n polytope from now on. To give you a few examples of a base for our simplex, a point is the base for a line segment. A line segment is the base for an equilateral triangle. An equilateral triangle is the base for a tetrahedron. A tetrahedron is the base for a 4-simplex, and so on. Now we can define the height of a n polytope. Height definition: the distance between the centroid of the base of an n polytope and a vertex not at the base of the n polytope. So we are now ready to determine the height of a simplex. First, we look at the base of an n simplex. We need to find its centroid. In order to do this, we need each of its coordinates. The easiest coordinates to work with are the basic vectors, which places a 1 in the corresponding coordinate of the set of coordinates for each vertex and 0 everywhere else. In other words, if we had an equilateral triangle as a base, our coordinates would be. Using the distance formula, we can see that these are in fact equidistant. I'm not going to do all three, but let's plug in values for the first two sets of coordinates. 0 came from the first number in E2, 1 came from the first number in E1, 1 came from the second number in E2, 0 came from the second number in E1, and 0 came from the third number in E2, 0 came from the third number in E1. So the distance is root 2. It would be nice though if the distance was 1. We can force it to be just by multiplying the coordinates by 1 over root 2, since root 2 times 1 over root 2 equals 1. This is called the unit length. Now we can have each edge be whatever length we want. Let's call it A. All we need to do is simply multiply the coordinates by A. Thus, we can rewrite the coordinates as Now that we have the coordinates for the base, we can find its centroid. All we do is add up all the values in the same coordinate in the set of coordinates and divide that by the number of set of coordinates. As you can see, if we add up all the values in the same coordinates for our triangle coordinates, we get A over 3 root 2. A general formula for this is C equals A over n root 2. The C means it's the centroid. This value corresponds to all coordinates from 1 to n. Now we need to determine the distance between the centroid and one of the base's vertices, what I will call the radius r. To do this, we can use a modified distance formula. For ease, let's choose the first vertex even though they are all equidistant. Here is a more general form of the distance formula as it relates to r. If we look at our first vertex, only the first coordinate has a non-zero value. Because of this, we can split the summation into two. So just to make room, I had to move things around a little bit, but this continues down here, and the first summation becomes the first term, and the second summation becomes the second term. This simplifies to, we now have a formula for the radius of the base. Finally, we can calculate the height of a simplex. Here we have a line segment. And these are two places where a third equidistant point can be placed. These 2 points actually lie on a line that is perpendicular to the line segment and bisects the line segment. Because the non-base vertex is both perpendicular to and bisects the base, we can use the Pythagorean formula to find the height. Let's solve this for h. If we substitute what we have for r, we get this is the height of an n simplex. Why is this important? Not only does the vertical line segment bisect the horizontal, but the horizontal bisects the vertical, meaning this half is the height and this half is the height. In order for the two places to be equidistant to the others, then twice the height must equal the length. Substituting our equation for height, divide both sides by 2a. Now we're going to square both sides. I'm just continuing over here. Now we're going to cross multiply. We're going to combine like terms and move the 4 to the other side. And now we're going to divide both sides by 2. And she'll bring us down here. What does this mean? The only way these points can be equidistant to others is if the dimension they were in was -2, which also means -1 vertex. And since those are the only two places an equidistant point can be placed, that is why 3 equidistant points cannot lie on a straight line. 4 equidistant points cannot lie on a plane, 5 equidistant points cannot lie on a hyperplane, and so on. I challenge you to determine the height of other polytopes. Is the height of a given polytope always constant for each dimension? I hope you enjoyed the video. Thank you for watching.